speaking will talk about generalized graded geometry and gravity.
Okay, thank you. And I want to start by thanking the organizers. Very wonderful conference, wonderful participants, lots of interesting discussions, and beautiful setting. Hope we can repeat that also in the future again. Okay, my topic is quite general, generalized graded geometry and gravity. Parts of it are ongoing work and previous work with Nicolas Mendoza, with Eugenia Boffo. There were other people, Fechtsen Ku, Jan Wysocki, Pranyu Yucho, and I talked with lots of you, and actually we're going to talk about work of lots of you. So that's what the dots are for. So Richard asked me to have at least first half hour introductory. So I'll try to do this. Start with some motivation. There's of course the obvious motivation that we've already heard from a stringy context. And that's really a rather old story. So the magic in string theory comes with also the Kuiper-Ramond field, antisymmetric field, and dilaton, so you have all of them. You have stringy symmetries, you don't just have diffeomorphisms, you also have one-form gauge transforms, etc. So that's one motivation to double up the usual geometry and look at some generalized tangent bundle. Which in this talk is going to be mostly the usual one, canonical T plus T star M, or short double T M. You can do that much more generally also. You can look at other stuff. We had that in the previous talks, like Friedrich Wallach told us about E7 exceptional geometry. I'm not even going to write down that tangent bundle, it's huge. And another very natural choice would be to look at higher forms. So let's say P forms. Etc. We will have a pairing here always, which in this case goes to the numbers. In that case would go to forms. There's also going to be a bracket, the Dorfman bracket, which can be twisted by a P plus 2 form. We've seen that all in the previous talks. And the whole idea of this is that it implements stringy symmetries in such a way, which is very restrictive, that you can actually get a target space approach to effective actions. To effective gravity actions. So just the structure itself is hopefully so restrictive that you get actions like ones that determine the equations of motion for the dilaton. Well, that's in a string frame, but in another frame gives you Einstein Hilbert gravity. And also the Kuiper-Ramond field enters here as H equals 2 dB. So you can take that as kind of a challenge. You use that structure, you build up a formalism of differential geometry, you crank the machine. As input you have G plus B. And as output you want to get this. It's actually quite challenging. For instance, it's challenging to get the 1/12 here and the correct factors in front of a dilaton. This has been done in the literature. I will talk a little bit about it. Another great thing is the dualities will transform G and B in some sort of complicated fashion, but in this language, it's just going to be the natural ODD symmetry that you get from a pairing which has signature D, D. So of a generalized metric. The underlying mathematical structure is that of a Courant algebroid. So you've seen that also in many talks already. We have an anchor map that takes us back from a generalized tangent bundle to the ordinary tangent bundle. We have a pairing and a bracket, which for generalized vector fields, which are sections of E, satisfy a bunch of axioms, and a very concise way of writing them down is that you have the anchor map compatible with the pairing. So I could write rho x on yc here, but it can be polarized, so I can also write rho x on yy. You can pull that inside, it becomes the bracket. And then there's another peculiar one, which has the same left-hand side, but tells you that this bracket is actually not antisymmetric. It has a symmetric part, and that's governed by, well, on the left-hand side, the same equation, and then 2x, y, and the third axiom is just the Jacobi identity. The Jacobi identity that tells you that the bracket is a derivation of itself and actually motivates to think of it as being some generalization of a vector, of a Lie derivative along vector fields. Actually, in the stuff that I'm talking about, this one is not going to be so super important. We will often not even assume it. But these axioms have some consequences that we would like to assume. Namely, they imply a Leibniz rule. So x, f, y, x acts on f with the anchor map. And then you can pull it out. That's a consequence of this, and I will always assume this. And lastly, another consequence is that the anchor map turns the Courant algebroid with Hoffman bracket into the ordinary Lie bracket. Just for commutator of vector fields. Again, this I will not usually assume. So we will have 1, 2, and 4. There's some further structure. A generalized metric. It can be formulated in terms of a map, Tor, which is self-adjoint and squares to the identity, and you can use it to split the generalized tangent bundle into a V plus and a V minus part, and in terms of Tor, generalized metric is when the pairing, and you put Tor in either one of the two slots like this. This can be used to fix the signature from D, D to 2D, or depending on what kind of metric you put in, also other signatures. So we have this structure, and in order to do any type of differential geometry here and describe gravity, we also need Courant algebroid connections. That map pairs of vector fields into vector fields and have the usual properties. But we're linear in functions in the, well, I can pull f out here, so it's f times the connection along X on Y, and if I put an F in front of Y, this thing acts on this with the anchor map. Okay, that's all the thing that we want to have, and then there's some obvious questions, of course. How to fix or how to find an appropriate connection like this in terms of the given data. Given G, B, phi. Sorry? No, given this data, how do you pick a particular one? So in fact, there's many choices, but you want it to be compatible. Oh, that's, yeah, I see. Yes, sorry. So this is supposed to be compatible. Most importantly, with the pairing. We shall always assume that, and later with a generalized metric and other stuff. Okay, so it will always be compatible with the pairing. We don't look at connections which are not compatible with the pairing. So that's always assumed here.
Just a little detail, what's the difference between the pairing and the generalized metric?
The tau.
Okay.
So if it's also compatible with G, then actually the connection will commute with tau. We'll get to that. Further questions? How to define torsion? How to define curvature? So first one that was answered a long time ago by Marco Gualtieri, who's in the audience. Just let me give the formulas. So if you just have that data and want to write down something that's tensorial and plays the role of torsion, you do the usual thing. But when you would like to subtract a Lie bracket, something antisymmetric, and the canonical choice would be the Courant bracket, which is just the antisymmetric version of the bracket that I've written down here. But then everybody knows this is not tensorial, but it can be fixed by another term, which involves the connection again. So I hope I've written that down correctly, and that makes the whole thing tensorial in all the slots. So I can put functions in any of the slots and pull them out. So that's a bit peculiar, this thing, and I'll have some more to say about this. In fact, you don't need to antisymmetrize. You can also put here the Dorfman bracket, and you can drop one of the two terms. Provided that the connection is compatible with the pairing, it will also automatically be antisymmetric at a somewhat simpler formula. I think that was in 2007, if I'm correct, or even earlier. How about curvature? So that's even more complicated. So from papers of you. I think that was 2013, but also Yochu, Wisoki, and other people. So I'm not going to write that out. So you take the naive curvature that you would get by putting in the Courant bracket. You take this minus thing, the entries exchanged. So you symmetrize, and I've got some questions about this that maybe you can answer later why you do this. And then there's correction terms that look a little bit like this thing. That make the whole thing tensorial. And since there was some by hand symmetrization, it also has some nice properties on the exchange of the first two and the second two entries. But here the question is, do we have some more user-friendly expressions for this? And we'll take a pedestrian approach here and actually get some nice expressions. This whole thing has also a graded geometry story to it. Look at the N, Q, P manifolds. You look at this bundle, which is the tangent bundle of M shifted in degree by 1, and take a cotangent bundle of the whole thing shifted in degree by 2. Local coordinates here are the coordinates on the base and dual to the momenta of degree 2, so degree 0. With degree 1 theta I that you can identify with differential forms, and also degree 1 chi i's, if you like, you can identify them with inner derivations. These together, just use a shorthand notation. I'm going to call them chi, and in this picture, the generalized vector fields would be degree 1 objects. Now, Henrik has already introduced that and shown to us how you get the pairing from it, how to get the anchor and the bracket from all that. So we introduce some degree 3 Hamiltonian. And then you have a dictionary. There's obviously a natural symplectic structure on it because it's a cotangent bundle. Corresponding Poisson brackets give you the pairing. And the anchor and the bracket. And by using the Jacobi identity for the Poisson bracket, just this alone will give you Courant algebraic axioms. One and two, and also the number 4 that I'm interested in. And if you impose furthermore that theta with itself has vanishing Poisson bracket, will give you the Jacobi identity. That was axiom number 3. You can also weaken that a little bit and just impose this thing on functions. And that gives you the property that the anchor map can be pulled inside the Grant bracket to give a Lie bracket. In all the gravity-related things that we will do, we will actually not need this. We will neither need this nor that. So in essence, everything follows from the Jacobi identity of a Poisson structure, so that's quite nice. Symmetries here are canonical transformations. And if you recall your analytical mechanics lectures, when you learned about canonical transformation, one particular one was the one that took x into p, and p into x, well, up to a sign, you exchanged x and p. So here we can ask a similar question. We have 2 degree 1 objects. Can we take this into that and that into this? And yes, you can. There's a canonical transformation for this of type 1, just like in classical mechanics. I'm just giving this as an example. All the other ones are kind of obvious. There's a type 1 canonical transformation for generating function depending on the old features and the new features, which is anti-symmetric. So it's equal to minus theta tilde theta, and so that would be the one that takes x into p, p into x in the usual case, and here it will exchange x and chi. Well, if you try to write down the most general thing that is of that form, given the data, you will have one part, just think of this as a vector, theta transpose, and you need some symmetric matrix, theta twiddle. So that will be antisymmetric, or you take 2 thetas, but then you need to put an antisymmetric matrix in the middle, and same thing for this piece. So if you're looking for a generating function of this type, which has the property that I've written down, this would be the most general one, where this is a symmetric matrix, non-degenerate. This one is antisymmetric. And well, if you compute the canonical transformation that's induced by this, this doesn't involve phi. You could put some phi in by modifying these guys. Good question. Anyway, you can guess what you're getting. It will define your new chi tildes and phi tildes in terms of the old ones. And the map is precisely given by the one that gives you the generalized metric. So these guys get multiplied by a matrix, which is G inverse B, G inverse here, G minus B, G inverse B, and minus B, G inverse on the bottom. I think this is quite cute. So in this setting, what I think is really beautiful about it, that everything follows from just Jacobi identity from the Poisson brackets, and you only need to look at canonical transformations and you get all the structures that we need here. Okay, so that's the first part of the motivation and introduction. It's kind of a general motivation for studying generalized geometry in the context of gravity and string theory. There's a second motivation, which is a bit more personal. It's the idea of introducing interactions by deformations. Well, in the context of gravity, we have a very beautiful picture that gravitational interactions, gravitational forces are simply free fall in curved spacetime. It would be nice to extend that to other forces. Of course, you can do that by Kaluza-Klein. There are also lots of problems. So if you want to do something like this for other forces, an idea is to, well, not think of like a free Hamiltonian in a curved spacetime, but instead deform the quantization conditions. Deform a Poisson structure, or after quantization, deform canonical commutation relations to introduce interactions. A simple example is electromagnetism, and when we would like to do it for gravity. Well, electromagnetism, you introduce the coupling of charged particles to other particles by taking the free Hamiltonian, so p squared over 2m, and replace momentum by the canonical momentum in it. But I don't want to do this. Instead, I want to keep the free Hamiltonian and deform the Poisson brackets and the commutation relations to introduce the coupling to A. That's actually very natural because if you look at the symplectic one form, gets deformed by adding A, and that implies that the symplectic 2 form is just the old one plus the electromagnetic field strength, and at the end of the day, it deforms the commutators of momenta, pi, pj, which are usually 0, become proportional to electromagnetic field strength. If you do this and keep the free Hamiltonian, compute the equations of motion, etc., it gives you the correct Lorentz force. And if instead of writing the usual p squared, you contract p with the sigma matrices, you even get the correct coupling to spin, etc. So you get the gravitation, you get the electromagnetic forces this way. And now the question is, can we do the same thing for gravity? And we try to do it very naively, then immediately we have a problem. We would like to deform the Poisson structure with a metric, but the metric is symmetric. Poisson bracket is antisymmetric, so we're naturally led to introducing Grassmann variables. So two Grassmannian variables and an odd Poisson bracket. We can deform that using a metric like this. You play around with the grading a little bit. You'll find out that these can be chosen to be degree 1 objects, and the Poisson bracket can be chosen to be a degree -2 object. You extend this whole thing. You want to keep that x with p is canonical. So since the Poisson bracket it's odd and of degree -2, coordinates should be of degree 0, momenta must be of degree 2. Keep going like this. You can construct yourself Poisson brackets of the momenta with the thetas. So that's degree 2, that's degree 1, the bracket is degree -2, so it should be linear in the thetas. So that's a reasonable ansatz. And in fact, playing around, you find that this is a connection, and due to the Jacobi identity, it's automatically metric with respect to this guy. Okay, so I've got 1, 1. I want this to be a function, should be degree 0. I forgot to write this here. And so 0, because I want the Kronecker delta to be degree 0. Yeah. So I didn't do the whole story here, but it's a really nice exercise when you're bored. Have an aperitivo, take a piece of paper. You can start from here. Everything just goes completely automatically. So you automatically get metric connections. You get curvature and all the other structures automatically. So this is quite nice. Sorry? Yes, okay. So taboo coordinates is like going from this deformation idea back to the covariant coordinate idea. And the two things are related. There's Moser's theorem. There's maps between the two. the maps have freedom, and that freedom is exactly what's called gauge symmetry usually. So all this stuff is just packaged in a different way into here. Okay, so for me, that's one of the motivations to look at it, and if you stare at that, it's of course extremely similar to this structure. Just a little bit more propaganda here, maybe. I don't want to take too much time. So it's a long story, but it's also completely canonical. It's easy to reproduce. Look at the equations of motion in that picture. So in the usual way, like this, and the Hamiltonian here is actually a quarter theta theta, where this is theta I pi, so I don't set it equal to 0. It actually gives me the Hamiltonian. Look at the equations of motion, gives you the geodesic equation. You do a slightly more clever trick. You get Matheson, Pepper, Petru terms to it that give a correct coupling to spin. And if you ever have done this in general relativity, it's actually really difficult to derive from in ordinary general relativity, but here it just goes like a cookbook recipe. You just crank the machine, you get all the correct equations out.
As you erase that action, I have a question. Does every solution to these equations of motion give you a Carnot algebra? Is that a theorem? Is there a theorem like this?
So what exactly did I erase?
So you erased an action involving phi and g and b.
Yes, that's a good question. Actually, I will comment on that.
Okay.
I don't know the answer, actually. Do you?
No.
Okay.
Sorry, can I ask a question? I mean, you wrote these brackets, but I mean, what's the status? To me, it looks like some of those type of reductions you can get from sigma model, whatever. So what's the status of those brackets?
Like, why did I write this down?
Yeah, I mean, I mean, to me, it looks like some type of reduction from sigma model.
Yes, surely. No, it's part of motivation. So I was trying to get this idea, changing, how can I say, changing, deforming the Poisson structure, or after quantization, deforming canonical commutation relations to introduce interactions. Motivation was so that you can describe all forces on equal footing. So you have just three Hamiltonians and you have deformed commutation relations. Gives you electromagnetism, gives you gravity. You can also do it for non-abelian gauge theories. So it's more like a physics motivation. I think your question is mathematically.
My question is that I recognize these formulas. If I would just do sigma model and Hamiltonian formalism,
Yes.
I get the version of these formulas, but it doesn't mean that I get the gravity.
Yeah, that's true, yeah. So that's not going to be a theory that describes field equations for the gravitational field. This thing will tell you how particles move in a given gravitational field. And then the question is, how do you get the field equations for gravity?
Can I just ask about this last point? So usually, you say for electromagnetism, if you have the metric which you use to define free Hamiltonian,
Yes.
then you can make this magnetic deformation in order to get the motion of magnetic particle.
Yes, 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 yes.
But now you're using the metric in order to deform the symplectic form.
Exactly, yes. So I can actually also tune it to 0.
Free Hamiltonian in that case.
The free Hamiltonian is written down here.
What structure gives rise to the free Hamiltonian? Because originally it was the metric that gave the free Hamiltonian.
Yeah, that's true, yes. So think of it more like this way how you get the Dirac equation from a Klein-Gordon equation. That's like a Dirac operator, and you square it, you get the Hamiltonian. So I skipped a bit of that story, but I'm happy to discuss it further, so there's some more stuff to it. I skipped quite a bit. Yes? Yeah. So actually, thank you for that question. So going to taboo coordinates, which would be a natural thing here, is exactly the same thing as going to local inertial coordinates in general relativity. So the two things are precisely related, yeah. So it's very beautiful. Metricity is just the Jacobi identity for the Poisson bracket here, so you don't need to invent new geometric structures, you just have algebra. Okay, anyway, this was part of the motivation. That's not going to be what my talk is about, so I skipped lots of details here, but I will continue in such a pedestrian way to now take a look at generalized differential geometry. I'm not claiming any novelty here. I'm just trying to take a pedestrian look at it and get the structures bit by bit. So we do want to have a generalized tangent bundle, which for simplicity, we take the canonical one, T plus T star. We want to have an anchor. And we want to have a pairing, which is sometimes also called eta. We want connections, which I already introduced, some generalized connections, which is compatible with a pairing. And satisfies the axioms that I've already written down. So let's see what we can get with that. If we just have that structure, we can use it to define the divergence. So something that maps generalized vector fields to functions and is compatible with the anchor map. In this way, we can define this to be, given such a connection, we can define the divergence in the usual way as the trace of a covariant derivative acting on x. If you're also giving a volume form here, which of course we will eventually need to write down an action, we have some volume form omega. There's a second formula for this thing. We take the Lie derivative along the vector field that you get by applying the anchor map to x of volume form. And well, if you have a volume form, you might as well ask these two things to be equal as one of the conditions. So given the volume form, you want connections that also satisfy that. But then you can try to introduce further structure, like torsion, curvature, etc. And let's just do that in a completely naive way. So we know it should contain covariant derivative along x of y minus vice versa, which is obviously not tensorically. So we can try to correct it. That's the correction term. Let's play naive. We don't know what it is. But the torsion should be antisymmetric, so this should be a skew bracket. And we want it to be, this whole thing to be tensorial, so let's say I put a function in here. Goes here, here, and here, and I want to be able to pull it out. Well, it will pick up a anchor map of x acting on f from here. So this implies second property And that's it. Well, how unique is that? It's unique up to any antisymmetric tensor. So if you have two of these skew brackets and you take the difference, you're going to get an antisymmetric tensor. That's the freedom that you have here. So look that up in the literature. These things actually have a name given by Bruce and Grabowski. What you get is called a skew algebroid. You can add some additional structure, which I don't want to do actually, but I want to mention it. If in addition, this skew bracket is compatible with the anchor map in the sense that you can pull it inside and get the Lie bracket. In that case, the whole thing is called an almost Lie algebroid. And in that case, the bracket is called the Dull bracket by Madeleine Joslin. So we are not going to impose that, and I will later, time permitting, I will later explain why we don't want to impose that. But in this context, I also want to mention some more stuff that Marlene did with this. She defined a Dorfman connection by the following formula. Take the anchor map of X, let it act on the pairing of vector fields Y and Z. There will be one term which involves her Dull bracket, and a second term which defines what she calls a Dorfman connection. She has some nice formulas also. The curvature of that thing is equal to the Jacobiator of the Dull bracket. So this thing in general will not satisfy Jacobi identity, but in the case that you have this additional compatibility with the anchor map, the Jacobiator is under control, just gives you the curvature of that connection. So I think Thanasis will tell us a lot more about things that are related to this on Friday. Curvature. And this somewhat more user-friendly approach where we introduce this additional structure, but we still need to fix it. Curvature just has the usual formula then. It's a commutator of covariant derivatives minus the covariant derivative along the skew bracket. You can define Ricci tensors in the usual way, and scalar curvature by contracting with respect to an appropriate metric. Let's take a generalized metric of Ricci, or so that depends on the connection, depends on the metric, or you could also contract it with a pairing.
So if your connection is compatible with PDM5, do you then get the right pressure function on the generalized connection?
Okay, so let's write down the action. That's a good question, right? So a candidate of an action that you can formulate in this context would then be integral over appropriate volume form. the scalar curvature. And the usual volume form like this. So do I get the correct equations of motion? Well, that depends a lot on what you choose for the connection here.
But I thought we have compatibility between the connection.
Sorry?
We have compatibility between the connection and
Yeah, I will get there. So you want this thing to be compatible with the pairing, you want it to be compatible with the generalized metric, and you want it to be compatible with the volume form, which involves the dilaton. So this will not completely fix this. There's still an infinite number of choices. But if you do it correctly, you get the correct equations of motion, yes. So in this user-friendly way of writing down the expressions, you do have also a causal formula. Which gives you a connection in terms of a generalized bracket, contortion, and non-metricity. But you derive from the usual way. So let me just write down one term each, and I can give you a complete formula in the coffee break in case you're interested. So you get terms which are like the usual one with the vector fields acting on the generalized, or on the metric, contracting the vector fields. The only thing that changes is that you have the anchor map in here. Then there's going to be contortion term and non-metricity. And there's also terms that involve the Schupp bracket, which look like generalized metric of the Schupp bracket in the first slot and Z and further terms like this. So this means that if you have given the Schupp bracket and generalized metric and an anchor map, you can impose contortion and non-metricity to be 0 and get some candidate for a Levy-Civita connection. So I don't hear any complaints from the audience, but this whole thing has a catch, so it looks like you get this uniquely, but the catch is that one of the most popular definitions of this Schupp bracket actually involves the connection, and when the dog bites its tail, so you have a formula for the connection, but it contains the connection itself, and then you can actually not use it. But there are also other canonical choices for this thing that don't involve the connection, and then you can use it to find the connection uniquely. So it seems all to boil down to what to choose for that thing. So we got the properties, what shall we choose? Well, a canonical choice motivated by the ordinary commutator of vector fields would be to choose some preferred coordinates and set the commutator equal to 0, and then extend the whole thing by the properties of that map. Friedrich Wallach wrote down a formula like this in physics notation. In physics notation, this kind of bracket that you would get would look like this. Of course, that's not a coordinate-independent notation. It just means you take the anchor map, you get the vector field that's acting on coefficients of y and vice versa. Give you this kind of choice. So it would be a natural choice. But as pointed out by Chris, this might not have nice symmetry properties under ODD, etc. Another formula that I can give if I write down explicitly the splitting into vector fields and forms. Would be to take a Lie bracket between V and U, and then introduce some auxiliary connection, and let V act via this auxiliary connection on one form eta minus vice versa. So this is actually found in a paper by Paolo Aschieri. Where is he? Francesco Bonecchi and Andreas Deser. So this will also do the job. That would be another canonical choice. But there are more. Anyway, in this pedestrian approach to generalized differential geometry, we eventually also want to have Lie derivatives. So we will need to have Courant algebraic structure and brackets. And there's a neat triple identity that connects three structures, and that is you have a bracket which defines the axioms of an almost Courant algebroid, so everything except Jacobi identity, but compatibility with the anchor map, etc. You can write that as the Schupp bracket that we've been talking about. And the extra term that you need is a generalized connection, like this. So any two of these will imply the axioms for the other one, and so you pick any Schupp bracket, you pick any connection, it will give you a bracket that satisfies the axioms of an almost Courant algebroid, or you take any other two and you get the other axioms. One particular one is compatibility of a connection with the pairing. It will give you anti-symmetry of a Schupp bracket, and you can work out all the other ones. So any two give you the third one. So you could do this if you have a Schupp bracket and you have a connection. You can do this to introduce the bracket. What most people do is the opposite. So in my work, I took the Courant algebroid bracket. I took the Schupp bracket to compute the connection. What's mostly done in the literature is instead to take the Courant bracket, the connection, to find the Schupp bracket that you put into all your formulas. And if you take that choice, so this bracket equal to Dorfman bracket minus the connection, you get the Gualtieri torsion, and you also get the Holm-Zwiebach curvature. So actually, a quick question, since Marco is in the audience: is this how you found this guy? Oh, okay. Same question to you? No, okay. Here, in this one? Oh, okay, I should say you have to symmetrize it. So you symmetrize the entries. So what problem you meant?
Yeah, I think I just remember that there was a problem.
But then the main question is how to fix the connection. So popular approach is the usual one, set torsion, non-metricity, etc. equal to 0, require compatibility with the divergence that you get from a volume form. But when a big freedom remains, but eventually when you compute with scalar curvature, as far as I understand, it's unique. So that's a good approach. You could try a Palatini approach where you take G, so it's essentially G plus B, take the connection with dilaton and possibly also the structure that goes into the Schupp bracket as independent fields. Compute the field equations and see what they tell you about it. Some usual Palatini formulation, if you impose metricity, you will get out that you get a torsion-free connection and you get a Levy-Schwitter connection. So the question is here, does it work here? So that was work that we did with Mendoza and also previously work done by Pranyu Yucho and Jan Wysocki. Our hope was that this Palatini approach will actually tell you what this Q bracket is and then tell you all the Courant algebraic axioms. So that this is no longer an input, but actually an output. Taking the bracket as an independent field is actually too strong, gives you trivial equations. But you get some compatibility conditions on it, and it's a work in progress, but it looks like you can in this way actually get the Courant algebraic structure out. So what else can you do? You can just forget about all this formalism and work directly with half densities. Which was pioneered by Pavel Cervera and Friedrich Wallach. Or lastly, you can look at deformations, which is my favorite approach to the topic. So you don't impose conditions, but you take a structure that has G equals 0, B equals 0, phi equals 0, and you use this data to deform your things and actually compute the connections directly. Oh, maybe I keep that. Let's take a look at the deformed graded Poisson structure, most general thing that you can write down. Functions of degree 0, generalized vector fields of degree 1, and actual vector fields of degree 2. And most general Poisson structure that you have is V on F is just the action of V on F. X with Y gives you a pairing, but not necessarily the canonical one. So deformed one. V on X is given in terms of a connection. So here the deformation gives you the data of a connection, and commutator of vector fields V with U gives you ordinary Lie bracket plus curvature. Okay, so here my idea would be to start with a canonical structure and deform it, and then read off the connection. Read of a derived bracket, see how the derived bracket has changed, and then So this approach will give you this beast, and as output you can get a connection out of it. But if you compute the derived bracket from this formula, so a degree-free Hamiltonian involving the anchor map and possibly also background fields can be written down in simple closed form. You get a bracket satisfying the almost courant algebroid axioms. If you impose an addition with theta is vanishing Poisson bracket with itself, you would have a Jacobi identity, which will put some good conditions on the last term, but let's not do that. Just take a look at this, actually. Never mind. The flux is here. Okay, it's a way of getting a deformed bracket by deforming the Poisson relations, and here I want to point out something. Well, if you set the Gualtieri torsion equal to 0, and you take a closer look at the terms that I have here, ignoring the fluxes, this thing minus the bracket is actually the Gualtieri torsion, so that's identical. So it gives you, in terms of a deformation, I think that's interesting. These two things seem to be related. Okay, how does the actual deformation look like? It's actually super easy. Yeah, in coordinates, take the degree 1 coordinates and multiply them by a Vielbein. To get new coordinates, you take this thing, this transformation to deform your Poisson structures. Will give you out a connection. It will give you a deformed bracket, and in particular, it deforms the pairing. So that the thetas no longer have vanishing Poisson bracket, but actually you find the metric in here. So that closes the loop to the things that I told you before about using deformations to describe gravitational interactions with particles with a given metric background. Now I just crank my machine. Compute curvature, etc. And you get the correct action, and I'm out of time. So to really quickly summarize this, generalized geometry is a great framework for gravity, for all kinds of modifications of gravity. User-friendly formulas exist at the expense of introducing extra structure. There's some more use of this graded geometry in the context of writing down field equations, like this multi-differential form thing that we did with Fanassis, and it would be nice to also curve that. Let me close here, and thanks for listening. Yes, yes, yes.
And I guess the whole formula was true except for the last one, right? Because that bracket will no longer be degree, it will be degree free. Minus. So that whole will be.
So the simple deformation wouldn't work, you say?
Well, I mean, the Poisson bracket is degree minus 2. Wouldn't be minus 2. So it seems that this deformation prefers the
Yes, 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 I agree with that. Yeah.
but the rest all goes to 2, I guess.
Mm-hmm.
What's special about 2 for gravity?
You have to think about that, yeah, but interesting comment.
I was going to ask, in this generalized setting, does it help with renormalizing asymptotic of the gravity, for example?
So it's also,
Is it more manageable?
so I don't have any answer for that, but I guess if you worry about renormalization of gravity, it's good to know classical gravity very well from all kinds of approaches and maybe find a formulation which fits more easily.
These extra fields tend to help.
So I have a question, which is, would you mind writing down your dictionary between GB5 and the generalized geometry structures? Like do you have a dictionary in mind that I'm just ignoring?
Which one you mean between?
Little g, little b, little g, big B, and phi, and the generalized geometric structure.
Ah. Okay, I didn't talk about phi, it would go into here. So I guess it's a question regarding the last blackboard. Yeah, so I gave you one of the relations here. So what else is going to change? These are the new features. So that's typically 0, but now it's equal to a connection. It's the Weizenberg that you get from that Vielbein. So I don't know the formula by heart, but I can show you later. So it's the usual thing, take this inverse times d of it. That's what you find here. Since it's Weizenberg, the curvature that appears between the vector fields is 0, so that doesn't get changed. It just have a Lie bracket. Yeah, that's it. So these are the only changes that you have. And with Weizenberg connection, once you put it into the triple identity, will give you a new connection which is not flat.
Many formulas that you use in this phase space look a bit similar to something what you get when you study quantization of particles or some structures similar to what you get when you don't apply quantization of potential. Is there any
Well,
quantized model behind the quantization of something?
so I would like to learn more about it, so maybe we can discuss more in the coffee break, and I think the answer is yes.
Another question. You mentioned something that's almost
Okay, so I could give this question back. So we want the axioms that involve the anchor map and the pairing. So we want this thing that controls the non-anti-symmetry of a bracket. We want compatibility of the anchor map with the bracket. We want the Leibniz rule for functions with vector fields. And that's it. That's it. Yes, exactly. Thank you, yeah. Yeah, so I don't want a pre-current algebroid, and I was. So since this is recorded. Yeah, So I was looking for your slides, but I didn't find them, so I didn't know what the name is. Okay, it's a metric algebroid, yeah.